In this slide, we'll study the most important signal in discrete time, the complex exponential signal. Ej omega n is the complex exponential with amplitude A. The complex exponential signal can be expressed through this Euler's formula: Ej omega n is cos omega n plus j sin omega n. It's important because the complex exponential is typically used in the Fourier analysis. In the Fourier analysis, we can decompose the signal into sum of cosine and sine. But as you see, cosine and sines are actually embedded within Ej omega n. And there is something called Fourier analysis using complex exponential. And this is what we are doing in this course. We are actually decomposing signals into complex exponentials, and not as cosines and sines, but directly into complex exponential, because this makes the computation and the calculation much easier. The other important thing about complex exponential is complex exponentials are eigenfunction of LTI system. What do I mean? If we have an LTI system and we have Ej omega n being sent into the system with amplitude 1, let's say, out comes the amplitude being changed by this LTI system, some amplitude Ej omega n plus phi, and that's all. So the original input, which is a complex exponential with amplitude 1 and with this frequency, out comes a change amplitude of the same frequency but of a different phase. So what we say is that eigenfunctions, when we passes through LTI system, the system LTI system only modify the amplitude and the phase, and it does not create any other frequency. So now let's go into the details of complex exponential. First, we introduce the Euler's formula. We'll just use this formula to say that E plus and minus j theta is cosine theta plus and minus j sine theta. What is E? E is the Euler's number. It's a constant, 2.71828, and so on. It's a real number. It is also the base of the natural log. Ej theta is called the Euler's formula, and we just need to memorize this. In our case, we are not going to derive this. We're just going to make use of this formula. Now, let's see a continuous time version first. Let us have xt is equals to 1 Ej omega t. It has an amplitude 1 and Ej omega t. So basically, we can express this as cosine omega t plus j sine omega t. And then t is real, and t grows from, let's say, 0 to infinity. Omega is a constant. Omega is the angular frequency, and it is radian per second. Now, what you will realize is that x of t is a phasor, can be represented as a phasor, and its length is 1 in this particular example. And it has a real part and an imaginary part. So we use the horizontal axis typically as the real and the vertical axis as the imaginary. And now we can now have this phasor such that along this it will be the real part at time t, and along this it will be the imaginary part. And you will see that the phasor is rotating. Depending on the omega, you will see whether it's rotating clockwise or anti-clockwise. If omega is positive, by convention it is rotating anti-clockwise. Okay, let's see some demo. Now we animate this. The phasor is, in our example, x of t. Its length is fixed. The length is the radius of this circle. It is moving at a constant rate of, for example, maybe 3 times a second. So it's 1 second, 2 seconds, 3 seconds, for example, and it is rotating in this. Along this axis, it is the real axis, and along this vertical, it is the imaginary axis. We can then also draw the cosine and sine like this. So the take-home message is that ej omega t is a rotating phasor, and basically it can be decomposed into two functions. One with respect to time, the real part, and the other part is the imaginary part. In the next few slides, we'll convert the real complex exponential into the discrete time complex exponential using time index n. So again, now this is changed into discrete time n, and omega is radian per sample as before in the sinusoid.